Good afternoon. We're still on portfolio theory. I think we may do enough to almost finish up today. Okay, let's do something. Let's include a risk-free asset into our portfolio. Up till now, we haven't included risk-free assets. And the risk-free asset will have a rate of return of RF here. We're going to call this guy R bar star P, and this guy sigma star P. Okay, so if we include a risk-free asset, what do? We draw a line from that risk-free asset till it just touches the efficient frontier. Now, this is the best way we can do, because if we drew it above so it didn't touch, then we couldn't include the risky assets. If we drew it below, then we would get a lower rate of return. So you get the highest rate of return if you're just tangent to that. And so let's write that out. Now, if we want to maximize order to maximize this angle of theta, let's write that theta here. Here. Let's call this theta, this angle here. So we want to maximize that angle theta here. In order to maximize R bar P, we must maximize that angle of theta. Well, this is equivalent to maximizing the tangent of theta. Maximizing theta, if we maximize the tangent of theta, we also maximize theta. And this gives rise to the so-called one-fund theorem. In the text, they talk about the two-fund theorem also, but why don't we just talk about the one-fund theorem? And this is due to James Tobin, (1958). And he is a Nobel laureate. So he got the Nobel Prize in economics for essentially this result. And what is this one-fund theorem? Let's state it. It says, an efficient portfolio efficient fund or portfolio P star can be established so that any efficient funds or portfolios expected rate of return R bar P and standard N risk we'll measure that risk by the standard deviation, sigma P, can be duplicated by a combination of the portfolio P star and what we really mean here is together with a risk-free asset. Okay. So this says all you need is one fund or one portfolio plus a risk-free asset, and then you can duplicate any other efficient funds or portfolios rate of return and risk by simply a combination of these two guys. Now this is a very important result. The implication of this result is the following. This implies, and this is important, this implies the so-called separation property. It says, this says that the portfolio selection problem can be separated into two steps. And these two steps are the following. First, we'll find the optimal efficient portfolio. Or fund, P star, and then to find the proportion of your budget to invest in P-star and the risk-free asset. So, and essentially, what you want to do here is the percentage of your, or proportion of your budget in P-star is related to your degree of risk aversion. P-star represents a risky portfolio. The risk-free asset, of course, is risk-free. So if you're very risk averse, you may have a higher percentage in the risk-free asset. If you're less risk averse, you'll have a higher percentage in the optimal portfolio. So that makes life a lot easier for us. And in fact, this is what happens in practice. In practice, a lot of brokers ask people, or they even give them a test to find out what their risk preference is. Okay. Now, let's see how to find this P-star. Okay, this optimal efficient portfolio. Let's look at this picture again. This is R bar P, sigma P. Okay, and what do we have? Let's draw the same thing we drew the last time. And here we're going to take, this is RF. We'll call this point R bar P star, and this is sigma P star. Okay, now what do we have here? If you look at this angle here is that angle theta. Okay. So to maximize R bar P, we maximize theta, like we said before, which is equivalent to maximizing the tangent of theta. Okay. And it's easy to calculate the tangent of theta. The tangent of theta is just what? It's just the rise over the run here, right? Here. So what is the tangent of theta? When we look at this, the tangent of theta, let's write it out right here. So the tangent of theta is the rise, which is R bar P star minus RF here, over the so-called run, which is just sigma P star. Okay. Okay. Now, to do this, to To maximize the tangent of theta, we set the partial derivative of the tangent of theta with respect to dwi, the partial with respect to the proportion we have in stock I equals 0 for I equals 1 to n. And n, what does n equal? N is this is the number of risky assets in our portfolio. And it's actually our optimal portfolio here. Okay. If you do this, and what we're going to do, we're going to say, let this be an extra credit problem. This extra credit is algebraically messy. Let's say exercise 10, page 142, or just say chapter 6. And that extra credit, we could have it due a week from today with the other stuff here. This is not so easy. If you like algebraic gymnastics, then maybe you'd like to do that. You obtain the following equations. And the book leads us through this. And these equations look like the following. You take the sum, I equals 1 to n, over all of our risky assets, sigma ki, lambda wi, equals r bar k minus rf for k equals 1 to n. This is equation 6.9, page 168. Okay. Then letting V sub I equal lambda wi, I equal 1 to n, for all our risky assets, we obtain by substituting into equation 6.9. Okay, we get the following. We get the sum, I equals 1 to n, sigma ki times vi equals rk bar minus rf, k equals 1 to n. Okay, now we're almost there. And I'll say the following. I'll say, now, simply, which is really not so simply, solve for the VIs. VIs in the n linear equations, and then normalize them to obtain our WI stars. That is, set WI star equal VI over the sum of the VIs. I equals 1 to n. Okay. And these W's correspond to our optimal portfolio. So that's how we found what proportion of each risky asset to put in the optimal portfolio. This is kind of messy. And you would never have something like this on an exam. Oh, speaking of exams, we typically, I think, I'm looking ahead, we'll probably have the exam sometime the week before our break or the week after. I'm leaning towards the week after the break. Okay, but if you have an opinion on that, whether you would like it the week before the break or the week after the break, please send your comments into Blackboard. Okay. So I think we're, okay, good. Okay, another thing we can do is to generalize our portfolio diagram. And what we mean by generalizing our portfolio diagram, to extend it to more than two assets. In our portfolio diagram lemma, we only consider two assets. Okay. So let's first consider three assets. And these three assets are 1, 2, and 3. Okay, we have these 3 assets. And let's look at what our diagram looks like. So we have our sigma p, r bar p, as we usually do. And let's say we have 1, 2, and 3. Okay, so now what we're going to get is something that looks like this, and like this. Okay. Now, instead of a triangle, we get kind of a figure which has curved sides here. And in here, we can do all kinds of things. Like if we take a combination, this side is combinations of 2 and 3. Okay? Here. In the middle of this, you can get combinations of 1, 2, and 3. And inside, like suppose you have some point in here. One, 2, and 3. Okay. So we scope out the whole thing. In here, in the red, we have the combinations of 1, 2, and 3. Along this line, it's a combination of 1 and 2. Along this line, it's a combination of 1 and 3. Okay. Now, suppose we have more than 3 assets. If n is greater than 3, we get a portfolio diagram like the following. Let's look at this. R bar P, sigma P, and we get something that looks like the following. We get something that looks like a bullet shape there, and then it goes like this. So we get this bullet shape. But it's kind of a strange bullet because on the back side of it, it looks like it has little half circles taken out of it. Okay, now let's do something something a little bit different that's not in our book, but is very, very important. It's not even in Bodie, Kane, and Marcus. In fact, it's not in many finance books, but it's very important. There's something called dollar cost averaging. Okay, and I'll shorten that by just saying $CA. I'll abbreviate that. And our key result on dollar cost averaging is the following. say investing the same amount of dollars in each period is optimal at least as good as good or better in terms of maximizing our expected rate of return versus purchasing the same number of shares of a stock or mutual fund. Now, this is very, very important because in most people's retirement account, you put aside with your employer a certain amount each month. And typically, you don't change the amount that you put aside each month. So you put aside a constant amount. And you don't tell your employer that you want to buy 10 shares every month. You tell your employer, say you want to put $1,000 in every month into your retirement account. So dollar cost averaging is the way most people do their retirement accounts. So it's the way most people invest in their retirement accounts. And it is optimal. The fact that it is optimal is very, very fortunate. Let's do some examples to show this. And this can be proved mathematically. But let's give a heuristic explanation. We'll give an extra credit problem on this. But we're not going to give it right now. In fact, we may or may not be able to get to it today. But a heuristic explanation or a qualitative explanation is as follows. Okay. When share prices are low, so we say when I say when in some period that share prices are low, dollar cost averaging purchases more shares for a fixed amount of dollars. And conversely, when share prices are high, our portfolio value is also high. Okay. So we'll see this. Let's do some examples. Before we talk about a proof, let's do some examples. Let's take some simple examples. Okay, good. By the way, the market seems to be on a tear today, or at least this morning, for a good job report here. It was down a little bit yesterday, but today it's well over 100, the Dow up. Okay. Suppose we consider a period equal 1 month, and see what happens for an interval of 4 months. We could say over an interval of 4 months. Okay. And we'll also say that our budget equals $200 a month for dollar cost averaging. Okay. Now for purchasing the same number of shares, each month, two, 3, and 4, we will set this equal to the number of shares that $200 purchases in month 1. Okay. So for dollar cost averaging, we have a budget of $200 each month. And for the fixed number of shares, we look at how many shares we buy for $200 in the first month, and we buy the same number of shares in 2, 3, and 4. Okay, so let's look at some data here. Okay. Let's say to case 1. We'll look at a number of cases. Case 1, we'll say variable share price that rises in the end. By that I mean near the end periods. Okay, so let's look at this. Let's look at month, price per share, in dollars, and number of shares purchased and dollar cost averaging. Okay. So we said we have 4 months, 1, 2, 3, 4. And what the price per share would be the following. Be $20 per share in the first month, $10 a share in the second month, $20 a share in the third month, and then $25 a share in the fourth month. Okay, so the price varies each monthly period, and it rises in the end. Okay. Now, we said our budget was $200. So if the share price is 20, we can buy 10 shares. If the second month the share price is 10, for $200, we can buy 20 shares. If the share price in 3 is 20, again, we can only buy 10 shares. And if the share price is 25, in the fourth month, we can only buy 8 shares. So in the end of the fourth month, we have a portfolio of 48 shares. Here. So it's the total number of shares purchased over the 4-month period. Dollar cost averaging. Okay. So dollar cost averaging purchases 48 shares. Now, let's keep this out. Hey, why don't we put a number on this page? It's 13. Okay. Now let's find the expected rate of return for dollar cost averaging. So why don't we say R bar for dollar cost averaging? Okay. Now the total value of our portfolio at the end of month 4 equals what? Equals 48 shares times $25 per share, because that's what it's worth, or the cost at the end of that month. So that equals $1,200. And our total cost equals 4 times 200 equals $800. Okay. The total cost is always easy to calculate for dollar cost averaging because you just multiply the number of periods by the amount you spend each period. So our rate of return and this shouldn't have a expected rate of return, so our rate of return in percentage is the following, equals what it's worth, the worth of our portfolio, $1,200, over the amount we spent minus 1 times 100. And this is 3/2. So we get 50%. So we have a nice rate of return on this dollar cost averaging here. Now let's calculate the rate of return for the fixed number of shares. And we can do that easily. Now let's look at R for fixed number of shares per period. And our period is a month. Okay. Well, let's calculate that. So in the first month, we purchased 10 shares for our $200. So purchase 10 shares. Let me say also purchase 10 shares in months 2, 3, and 4. So we're going to purchase 10 shares in each of those months with the same number of shares. Now, let's calculate the value of our portfolio at end of period 4. Month 4. Okay. So what do we have? We have 4 months. This is easy to calculate. Times what? Times 10 shares per month times $25 per share. So we see this is dimensionally consistent, and this equals $1,000. Okay? The 40 shares at $25 a share is simply $1,000. And what's our cost? What's our cost? Cost equals, if we want to buy 10 shares a month, in the first month it costs us $200 because they're $20 a share. In the second month, it costs us $100 because they're only $10 per share. In the third month, it costs us $200 again because they're $20 a share. And then finally, in month 4, the shares are at $25 a share, so $200 will buy us 8 shares. Or to buy 10 shares will cost us $250, okay? So this is the amount if we want to buy 10 shares each month. So this equals $750. Okay. So the rate of return, R, equals what? Equals the value, which is 1,000, over our cost, 750, minus 1, times 100. And what we have here is what? What we have here is 4/3 minus 1. So this equals 33 1/3%. Okay, which is less than 50%. For dollar cost averaging. Okay. So it's positive, but it's less than we would get by dollar cost averaging. Let's do at least one more example. Well, good. Yeah, let's do another example here. Good. Okay, let's look at case 2. Let's again think about variable share price that falls at the end. Okay. Okay, and again we're going to do month. We're going to do price per share. In dollars. And we'll do the number of shares purchased by dollar cost averaging. Okay, so what do we have? Say 1, 2, 3, 4. We have 4 months. And we'll say the price per share in the first month is $20. It's $25 the second month. It's $20 the third month. And it falls at the end to $10. Okay. So now, in dollar cost averaging, we have a $200 budget a month. So when it's $20, we can buy 10 shares. When it's $25, we can buy 8 shares. Again, $20, we buy 10 shares. And now when it drops to 10, we can buy 20 shares. So the total number of shares that we buy equals 48. Here. Okay. So this is the same as case 1, the number of shares that we bought. But the difference is, of course, is that the way the price varies per month. Obviously, if the price didn't vary per month, there would be no difference between dollar cost averaging and purchasing the same number of shares. Okay, so let's look at, first let's look at the rate of return for R for dollar cost averaging. Okay. And this is relatively simple. Again, what we're going to do is we're going to look at the values at end of month 4. And this is simple to calculate, so it equals 48 shares times $10 a share so it equals $480. Okay, now, what is our cost? We spent $200 a month here. Equals 4 times $200 equals $800. Okay, so our rate of return equals 480 over 800 minus 1 times 100 in percentages equals minus 40%. Okay? So now we get a negative rate of return here, but let's also look at the fixed number of shares. How are we doing here? We could do it. We might be able to skim it in. The fixed number of shares, okay, and here we're going to pick up, we're going to buy 10 shares a month, so we get the value equals 4 times 10 times $10 equals $400. And our cost is what? The first month is 200. This is month 1. The second month is 250 because the shares cost $25. The third month is $200 again, and the fourth month is only $100. So this is 3, 4. So our total cost here is $750. And therefore, R equals 400 over 750 minus 1 times 100 equals minus 46.7%, which is less than 40%, minus 40%. So even though on the dollar cost averaging gave us a negative rate of return, it still did better than the fixed number of shares. We'll do a couple more cases, and then we'll talk about how to prove this mathematically. Thank you. Hey, listen, have a great weekend. We'll see you on Monday.